I want to talk about high performance computing. A lot of what we've done up to this point has been computing in the small. So computing on a laptop, computing on the desktop. But one of the reasons we've been doing these things with the command line and with Linux as a way of interacting with it is because that workflow allows you to interact on much, much larger machines. Now today, that includes cloud computing, so the Googles and Amazon Web Services and Azures of the world, which still require a lot of Linux sort of knowledge to really use effectively. And the other category would be high performance computing. So these are the supercomputers that are out there. Supercomputers are definitely still a thing. A person doesn't buy them, but an institution buys them or a government buys them. And we use them, and they're essential tools to be able to do science in the modern world. One of the things that a supercomputer gives you is the ability to do parallel computations. And so I want to give you a flavor this morning about what that even means, what it looks like, and what does it mean to program a computer in parallel. Okay, so first thing is, what do we mean by a parallel computer? Actually, today, you are probably all carrying around parallel computers. I'm just trying to think if I can get the sizing of this. Maybe you can resize your own screen. Okay, so what is a parallel computer? So almost all modern laptops are actually parallel computers now. So even a low-key sort of laptop will have 4 cores or 6 cores or 8 cores or whatever it is. When we talk about supercomputers, we don't really mean 4 cores. We don't even mean a few thousand cores. We typically mean hundreds of thousands of cores. So think rooms which are just filled with racks and racks and racks, and each of these racks is filled with computers. And each one of these computers, every sort of slot you see in there is a full-blown computer that probably has 20 or 30 or 60 cores in every one of those sort of pizza sliced boxes and all the way through. These supercomputer centers, they need to worry about things like cooling. There's a lot of computers that generate a lot of heat. So a lot of the infrastructure of a supercomputing center is just to keep the whole thing cool and to provide a network or an interconnect between all those different computers. But they exist at different scales, right? So you can have parallel computers of a single machine, sets of machine, or whole rooms full of machines. Each computer itself, each chip, is actually not fundamentally different than what you probably have in your laptop or your desktop. In addition to supercomputers and cluster computings and things like that, we also have parallel computing in the context of graphic processing units. So there's a whole branch of scientific computing which takes advantage of the fact that GPUs, graphic processing units, actually have hundreds or even thousands of cores built into them. So when you're doing graphics processing, there's a lot of things you've got to do again and again. There are ways of programming your graphics processing unit, the video card, to actually do meaningful work. That's a type of parallel processing. And even furthermore, phones nowadays are all multi-core type things. They've got 6 processing cores or 8 processing cores. A core is like a CPU, but there's just multiple ones, depending on the architecture. Okay, so when we talk about these multi-core processors, right? So whether or not be the iPhone 10 or a GPU or the Samsung Galaxy S8, this is sort of the architecture which is on the disk. So at a higher level, when we talk about a processor, right? A processor is a piece of silicon, integrated electronics, and inside of it is going to be something we call the processor. There will be the actual processing unit, all the transistors that make up the logic that lets you do arithmetic and control and memory access and things like that. And then there'll be a little bit of memory, which is actually on the processor die itself. And we typically call those L1 cache and L2 cache, maybe L3 cache. Basically, these are a little bit of memory, which is physically very close to the core. L1 cache is typically a tiny bit faster than L2 cache. And then those things inside this box, which we call the processor, is linked to the RAM or the memory of the machine all together. In a multi-core processor, which is now almost standard, right? Like most machines are dual core, quad core, octa-core, or many more. The processor, a chip inside the computer, actually has inside of it multiple computational electronics which are independent in multiple cores each one of those cores will have their own cache. A cache is just a little bit of memory, which is close to a processor core. And this is sort of where the idea of L1 cache and L2 cache start to make a bit more sense. L1 cache would be memory that's used only by core 1. This L1 cache is used only by core 2. L2 cache is available to both those cores. And those are still memory which is independent from RAM. So this is all multi-core processor kind of stuff, right? And in terms of how we typically use it, right? If you're running, the reason your computer has a multiple cores is so you could do more than one thing at a time, right? We deal with multitasking, multi-threaded computers, right? You're running multiple applications in the background. And so this lets the operating system spread the load that's on a computer among multiple processors, so it all runs faster. When we're talking about parallel computing, we're talking about running one program over multiple cores. So this is a little bit different than what an operating system doing with multitasking, right? Where you have 2 or 3 or 4 programs and you want them all to run, and the operating system just sort of figures out a way of separating them out. Of course, if you know about operating system design, you know that the operating system itself is a parallel program. But if you are writing your own program, there are ways of writing it so that your one program can actually utilize more than one core at the same time. And so that would be an example of parallel programming. Parallel programming is a kind of programming that falls under concurrent programming, but we'll focus only on the parallel part. When we talk about high performance computing, we don't really mean 2 cores or 4 cores or 8 cores. What we really mean is sets of processors. So not just a single processor with so many cores. We typically are talking about something more like this. We've got a number of different nodes, and a node you can think of as a physical box, something with its own power supply, its own hard drive, its own memory, and a network connection. So you can build a compute node just by taking like the computers in a classroom. Every computer is its own node. They each have so many cores on the CPU. They have their own memory. They have their own disk, and they're connected all together through a network, right? This is what we mean by a cluster. When you treat a number of machines as a computational unit altogether. So you could build a cluster, and this is sort of what people do. You could have 10 different computers. Each computer has 224 cores on the machine. And so and maybe even node has 2 physical processors on the board. And so you could have 240 processing cores, a 240 core system. And so that would be a very small cluster nowadays. And what you do is you connect those things through some sort of interconnect. You're probably familiar with the word Ethernet and gigabit Ethernet and things like that. When we're doing this, and we're passing information between it, there's a certain amount of time it takes for information to be transferred from one compute node to another compute node. So there are other technologies out there for doing inter-node communication that are much faster than Ethernet all the way through. So one of those would be something like an InfiniBand backbone, and there are many others. But you start to get throughput on the order of tens of gigabytes or hundreds of gigabits between it. And these connections are usually designed so that any node can talk to any other node at that full capacity, and they can all chatter between each other. So when you talk about a supercomputer, the actual speed of the core really isn't that important. Often your computer on your desk will, per core, be a faster computer than what is in these supercomputing centers. Now, these supercomputing centers, they're not going to be shabby, but they just may not be the most extreme version of the CPU. What gives them their power is the fact that there's lots of them, and they have an interconnect, that is the network that connects them, that's incredibly fast. Low latency, you're able to push a lot of data. That's what makes, the interconnect is what makes a supercomputer a supercomputer. Okay, large clusters, right, basically have this topology of a bunch of compute nodes that are linked together. They just do more, right? So you've got a cluster and they're linked all together, and then all of them are linked together in sort of this topology. And that's sort of what you get in this kind of configuration. So here is a supercomputer. Every one of these racks, right, top to bottom, all these computers probably very close together in a network topology sense. the entire row is together in a network topology sense, and all the different rows together are a little bit further away in terms of network topology, the amount of microseconds it would take to send information back and forth. I mentioned it a little while ago that there is sort of a way of tracking what the current fastest supercomputer is, and you typically go to the top 500 list. So this is a 2017 thing, so let's just jump over and see what it is today. So top 500, the list. Okay, so as of today, let's take, we'll look at June 2020. Okay, let's go down to the list. Okay, here we go. Japan currently holds the record of the largest supercomputer in the world. This thing has 7 million cores that are all connected to each other. The United States has a couple of machines at a couple million cores apiece. It's not really, again, the number of cores, it's how fast they can do computation together. So this one down here, this machine in China, has 10 million cores, but it's not as fast as the other ones. That's partly because of the clock speed of the cores, but it's also related to the interconnect between these machines. And you can see that when they describe the computer, they give it a name, they tell you what kind of CPUs it's running, and then they tell you what kind of interconnect it's using. So for the Summit machine, it's running the CPUs or IBM Power 9s, running at 3 gigahertz, and it's running as a interconnect, a dual array Mellanox EDR InfiniBand. That's how it's connected. So those are the features that sort of put it together. And computers nowadays often have GPU type compute things on them as well, which is why you're seeing NVIDIA all the way through here. So today, a big computer has hundreds of thousands of nodes, but really even tens of thousands of nodes is what the scale is. So how do you go about writing software that would take advantage of this kind of architecture? Let's say you had access to one of these machines, how would you use it? And so in particular, when I mean access to these machines, you might have heard of Compute Canada, and you might have heard of AceNet as sort of the Atlantic branch of what it is. We within Canada have access to advanced computing. High performance computing is a kind of advanced computing that I want to talk about here. The cloud is also a form of advanced computing. So there's a number of systems that are out there that we can use. So Memorial University itself has a 2,000 core computing cluster. Okay, so it's not giant on the world stage, but it's still 2,000 cores. It ain't too shabby. On the national system, there are a few machines. Also, I'll flag here the Cedar or Graham as being fairly big ones. So Graham, which is physically located at the University of Waterloo, it's got 20,000 cores all the way through. So it's not, it's in the, I'm not even sure these even make the top 500 list anymore. They're good sized clusters. And you as members of a Canadian institution, you're working with supervisors, the supervisors can get accounts on Compute Canada, and those supervisors that can sponsor you to interact with these systems. So if you're working on a problem that could take advantage of thousands of cores, it's out there. The technology is out there. You yourself don't go onto the system and register. You have to have some affiliation with the university, but you all have an affiliation with the university. So depending on the research you're doing, if you're involved in research, you can get access to this kind of system. But we'll keep it general for now. AceNet and Compute Canada aren't the only networks out there. There are lots of them. Okay, so here's where we're at in terms of the growth of computing power over time. Now this slide only goes to 2017, but it sort of continues on. Basically what we're looking at, and the scale here is the first one in the list and the last one of the top 500 list. So the actual, like the best computer that's out there and the 500th position computer out there. It doesn't matter where you are, they're both increasing on this semi-log sort of plot. So they're increasing, this is a logarithmic scale on the vertical, in this sort of power law relationship. And if you treated all the computational power of all the computers together in the world, that also is a thing. So if you go 20 years ago, the total world could barely do 100 teraflops. 20 years later, We are 1,000 times faster in terms of computational power, 1,000 petaflops, and we're sort of probably in the exaflop world now. So total amount of floating point operations, that's what a flop is, we're able to do that all the way through. Now, your computer, it by itself will sit down here somewhere, right, in the gigaflops, which is still not too shabby in the sense that a single computer nowadays has the same performance as something that would have been on the supercomputer list back when I was in university, right? This is the craziness of computation. So I went to university here. This was my undergrad sort of period right in here. Having a computer today would have made it fast, would have the desktop, like, and this is a mid 2017 laptop, beat half the computers on the top 500 list. It's staggering. It's amazing. Okay, so when we have this technology, when we have all these things, how is it getting faster? It's getting faster not because the CPU itself is getting faster. It's getting faster because we've got more cores, we've got more processors, and we can take a program and split it up over multiple cores and make it go. How do you do that? What does it mean to run a program in parallel? Okay, so there's two main applications people use for HPC systems, high performance computing. One is to take a problem, which is a certain size, and solve it much faster than with a single processor, right? So ideally, in some wonderful world, if every time you added a processor, it would run that much faster. So it would run n times faster when you add n processors. So maybe you could run a program, and after you parallelize it, changing the software so that it runs in parallel, it takes a 365-day problem and turns it into a one-day problem, right? So that's pretty awesome. It can take a problem which could have taken a year of compute and shrunk it down to a day of compute. It doesn't actually change the number of cycles required. It just changes how much time you and I need to wait. So rather than us having to buy a computer and leave one computer running for 365 days, we borrow time on 365 different computers, run it for one day, and then let someone else use it. This model is really what high performance computing is all about. It's a shared model of how to compute. And it's really what the cloud is as well when you talk about the Googles and Amazon Web Services and Azures of the world. You don't need to use all of the computers all of the time. You just need to use some of them when you need it. So it takes the same amount of energy to do that computation. We're just able to get it faster because we're spending that energy at a higher rate. The other thing that HPC systems can do is let you access more RAM than you would normally do. So even if you don't need the problem to be faster, RAM can be expensive. And so like a single computer, like you may have an 8 gigabyte system, or maybe you've upgraded and you've got a 32 gigabytes of RAM on your laptop. Supercomputing clusters, typically their nodes may have 128 or 512 gigabytes of RAM on a node. If you have a 100 node system, you actually have 12 terabytes of RAM accessible, right? So when problems work well with given a lot of memory, you're able to do things with terabytes. I don't know if there's been very many petabyte memory systems, but definitely multiple terabytes of RAM is a thing. You could have a large RAM dominated algorithm, and you need that. That would be a use for high performance computing. When we talk about parallel algorithms, there's a few ways of doing it. This is something you would cover if you took a course in concurrency. So if you come from a computer science background, you'll be familiar with this, but basically we talk about parallel algorithms. There's the embarrassingly parallel ones. These are the ones where you don't really need to worry about communication between processors. So you may have an algorithm and you just want to run it again and again and again, but change the input parameters, right? They're all separate. Rendering for video frames, you know, all these animated movies? Well, when you're animating a scene, that scene is independent of all the other scenes in the movie. So multiple computers can work together to render the whole movie that much faster. And all of the stuff that you do in terms of proof of work and cryptocurrency and Bitcoin are embarrassingly parallel type systems. This is why graphics cards are used so much when people want to mine cryptocurrencies. There's also algorithms that require communication. between the processors. So coarse-grained communication means that every once in a while they have to exchange information. So if you were doing an algorithm like solving a weather model or a climate model, you may solve for what the winds and the pressure and the temperature are in a region of the Earth. And then what will happen is it will exchange information about what neighboring cells or neighboring grid points in the ocean are between processors, and then run again. Fine-grained parallelization is when we're trying to actually write an algorithm that uses the computation itself is parallelized. So you could write an algorithm that assumes you can do multiple adds and divides or multiplies simultaneously and combine their information together. In terms of software complexity, it gets more complex as you go down the line. Okay, embarrassingly parallel stuff are actually quite easy to set up and run. Fine-grained parallel stuff, concurrency is hard. Concurrency is the idea of having one program with multiple simultaneous lines of computation. Concurrency is hard. There's no way around that. You got to worry about different locks and threads and different models of computation. I just want you to give a flavor of parallel computing. So we're going to sort of stay up in this category right here, but people definitely do get down in here when they want to run something very efficiently. Okay, so let's talk about embarrassingly parallel computation. What that means is, imagine you had something where you had to do a computation. So let's say you were compressing files. Okay, so I give you 1 billion pictures, and you have to take each one of those pictures and compress them to a smaller form factor. You're working for Facebook, and Facebook people are always uploading photos, and you need to take those photos and compress them into some way. Well, the order in which you compress them doesn't really matter. Each photo itself, you just need to compress them. If you had a single computer, you could compress the first photo, then the second photo, then the third photo, and so on. If you have multiple processors, so you had 5, each processor can compress its own photograph, and then the next set of time, those 5 processors can do 5 times as many. If this is the pattern for your algorithm, we call this an embarrassingly parallel computation, right? It's the perfect scenario. 5 times as many processors, it goes 5 times as fast. That's good. When you are parallelizing an algorithm, what you try and do is you try and parallelize the slowest part of your algorithm. It makes no point to parallelize something that only takes like a microsecond to run anyways. It may not be worth it in terms of the effort or the added communication. You identify what the slowest part of your computation is, and then you try and parallelize that all the way through. So let's say that you had 2 parts to your program, okay? There was part A and part B. You can think of it as 2 functions, function A, function B. So you do stuff, you do stuff. And you may choose or figure out that through a lot of effort, you can parallelize part number B, and you can make it 5 times faster. But it's a little bit harder to parallelize part A. You can only make it twice as fast. So you might feel really happy that you made B 5 times faster, right? But the reality is, making A twice as big has actually had a bigger effect on the overall running time of the algorithm. So you focus your energy not so much on what you can do faster, you focus your energy on the part that takes the most amount of time. And this means you have to measure performance, and you have to look at actually how fast code runs, optimize the slowest part of your code. It's not all roses. There is a cost to all this kind of stuff. And one of the things about parallelization is it's never ideal. Even if you were a perfect parallelizer, there's always some little bit of the code which can't be parallelized or can't be parallelized super efficiently. And so what happens is you get this thing called Amdahl's law. And I'll show it to you as a graph, and you can see the equation here. But here's the idea. Let's imagine that I'm able to parallelize 90% of my program. So of all the lines of code, 90% of them are running in parallel. That means that 10% of the program is still running in serial. This could be loading data from the disk. It could be setting up the interprocess communication. This could be summing the numbers together. What that means is when the number of processors is between 0 and 10, the speed up the ratio between how fast it was going in parallel to what it would cost in serial increases well, but quickly flatlines. For a program which is only 90% parallel, really, once you're at more than about 100 processors, there's no additional speed up. Now, it doesn't mean it won't go faster, right? So speed up doesn't mean how fast the program goes. It just means how much more benefit are you getting by using multiple processors all the way through. It's a ratio of like the number of processors you're using. You typically would take this speed up and divide by the number of processors to see sort of the actual efficiency. So things might be going faster, but if you're spending more and more CPUs on them, that's not a very good use of your time. If you can parallelize 99% of your program, right, you're able to get a much faster speed up. You're able to utilize more cores to be efficient. So when we're talking about these programs or these computers that have 100,000 cores, right? If you're talking about a CPU that has 100,000 cores, see this graph right here? That'd be like to the right, 10 to the 6. You need that program to be incredibly highly parallelized to take advantage of that architecture. There's no point in parallelizing running a program on a 160,000 CPU machine that's only 50% parallelized. It just there's no value in doing it. It's better used. Just go buy more computers. Don't use a highly performant, super expensive supercomputer to do that. Okay, so these are just things to be aware of, and I got a demo of that later on. How do you actually go about coding this? What does it mean to program in parallel? So let's imagine, and we're jumping ahead maybe to some point in the future, you are hired by somebody who's got that on the upper floor. You were told, here's your computer. You have access to this. Go do stuff. And you're like, okay, what do I do? Well, not for sure, but almost for sure, you will be using something called message passing. The message passing interface is a standard and portable way of communicating on a parallel computer. I talked about that each computer has its own RAM. You need to be able to send data between the computers back and forth. If you've ever heard of the network convention TCP/IP, that's another kind of way of communicating, but it's very slow. It's very bulky. MPI is much snappier. Each message is shorter all the way through. And it's a standard for how computers can communicate between nodes. And so software uses the MPI standard as a way of sending data between these different nodes. Now, the standard has been implemented a number of different times, but the library routines all have the same basic name. And typically you write these programs in C or C++ or Fortran. And there are different implementations of MPI. OpenMPI being, I think, what you'll end up as being most common today, MPI-CH, and then there's a number of vendor-specific implementations. And as you're learning about this, there is actually an MPI for Python. So what this is some Python bindings which sit on top of the C or Fortran versions of the standard. And we're going to do a demo with this. This is just wrapping these lower level function calls. So the fact that it's in Python shouldn't scare you too much. It's definitely a way of writing a program that takes advantage of multiple cores. So you can use MPI even for a smaller system, like a 4-core and 8-core laptop all the way through. Okay, so here's what an MPI program feels like when you run it. So normal programs have a first line, second line, third line, fourth line, and they go through. In an MPI or a parallel program, here's what's typically going. You've got a number of different processors, okay, or lines of execution. So different cores, process 1, process 0, process 1, process 2. At every point in time, each process might be doing something. So let's say for the first second of the program, process 0 has some data. This could be like the initialization data or the input parameters. Process 1 and process 2 don't actually do anything for that first bit of time. But number 1 reads in the data, say, from a configuration file. Then what MPI is, the message passing, is it passes some data. You do an MPI call, and you take that data, and you send it to process 1, and you send it to process 2. So now all 3 processes have some data to work on. Could be a configuration, could be a photo, could be some binary, could be something, whatever it is. Then you can have a parallel algorithm where each computer, either on its own or via communication between each other, so this would be a finely grained parallelization, are doing computation and they're exchanging data back and forth between each other. Then maybe you have a part of the code which is embarrassingly parallel, right? Where they sort of send data between each other. They all do their part with no communication while they're doing it. But at the end, the answers, the results of part 3 and part 3 from these 2 processors get sent back to the first processor. And maybe this last part is print out the information to the screen, save it to the disk. So those things are not parallelized all the way through. So this would be sort of the flow of what a parallel program is doing. It's divvying up the work all the way through. These arrows represent message passing ways of doing it. We consider all of the processors in our system that we're going to talk to as a communicator. So a communicator is just a logical group of a bunch of processors, and which within these processors, what we do is we give a number to each one of the processors, and this is what's called a rank in MPI jargon. If you have a single processor, a single communicator rather, then all the processors are just numbered from 0 to 15. You can, in MPI, set it up so you can have multiple communicators. So you can take those 16 processors and spread them and divvy them up into 4 communicators, which are sort of like logical groups. So you could have communication between these 4, communication between these 4, communication between these 4, communication between these 4. MPI understands this idea of multiple groups of processors. However, in our example, and in many examples, this picture on the left is sufficient. Just treat all processors as being part of the same group. Any processor can send data or communicate with any other. A process can actually be part of more than one communicator if you need it. So often what you have is the same processors that are all part of the large communicator, and then each separate ones all the way through. When we talk about communications, there's 2 types of things you can do. One are point-to-point communications, and then there are more collective communications. Send, so this is called an MPI send or an MPI receive. What that is a function call that takes some data from one process and sends it to another process. To receive that data, one program needs to call the MPI send function. Another processor needs to call the MPI receive function at that time. This is called a blocking operation in the sense that when MPI sends, it actually sits here and waits until this program also calls this receive command to get the data. So if this processor here has hung or it's doing some other work and hasn't yet called MPI receive, this program will just sit and wait. It will look like it's paused until it's done. Once it does that, programs continue, and then this one could send the information back to the process 1, but again, it's going to wait until the data is actually sent before it continues on. Likewise, when you call MPI receive, this function can't finish until process 1 has actually sent the information back. It's like talking on the telephone, right? You can't keep on talking until the other person has heard you and then said something, and then you get to respond, right? There's another way of doing communications, which is called non-blocking. And these are I send and I receive. And I send and I receive, when you I send something, you just send it over the wire and keep on going. This is much more akin to communicating through the mail. I write you a letter, I send it in the mailbox, I send it to you, and I go about my business and I start doing more computation. You receive it whenever you want, right? Do some stuff, and then you can send your response back to me and go about your own business. So these are non-blocking things. These are examples of peer-to-peer. I want to send some information, numbers, from one machine to another machine, point to point. There's another class of communications which are collective. I want to take some information from one node and send that same information out to all of the different nodes. That's called a broadcast. Or scattering, which means send some information to process 1, some information to process 2, and all the way through. And the reverse of that is called a gather operation. All of the processes suck information together. Basically, it's the reverse of a scatter, taking information from a bunch of processors and bringing it all together. Okay, this is a very high-level discussion, and I think it's helpful to actually see some MPI to dig into what this all means. So I've got a little notebook type that I've worked on here. I don't know how long this is going to stay up, but I'll put this here. I just created a little repo of some examples for this lecture, so I'll throw that up on Slack for your reference, but just follow along with me for a moment. Okay, parallel computing with MPI, right? So what we've done, I guess I've just adapted this lecture from somebody else. We've just gone through this tutorial of parallel computing. MPI for Pi is the library that we're going to use to set this thing up. So what we would typically do, I think it's best if I do it like, go. Okay, so you would do something like MPI for Pi, and it would install whatever you need to run this. And specifically what it's installing is the libraries, the underlying software that lets you do MPI on your machine. Okay, there's a ton of documentation. You're welcome to go over to the MPI4 docs if you want them. But the idea of MPI for Pi is it's implementing the MPI standard, right? The MPI standard, if you get into this stuff, you probably should be aware of the standard and refer to the standard. The standard's written for C and for Fortran, but the Python version is equivalent. So a lot of this assumes you know something about MPI to be able to get into this, but we won't do very much. And I think you'll be able to follow along. What does it mean to run a program in Python? Python is not multi-threaded by default. In fact, Python really is pretty poor at multi-threadedness. It's got some feature inside of how it works that threads don't really even work. You only have serial programs. A serial program is not a parallel program. A serial just means we do one thing after another in order. If you actually want to run a Python program with MPI or in parallel, you can't just run the program with a script. You can't just say Python script.py. That wouldn't run it in parallel. You actually have to run it with another program, namely MPI run, right? That will take whatever's after here and run it on so many processors. And what you do is you pass MPI run an argument, and you say, I want to run this program over 4 processors. So MPI run, this bit right here, it's part of the MPI standard, is how you run whatever program you want to do in parallel. Whatever goes here is the executable, right? This doesn't have to be Python. It could be a C program you compiled or Fortran. When you're running on these supercomputers, this line is needed to initiate the program. This is how you go. Now, on some computers, it may be called MPI exec, which is similar but not quite the same. It's that kind of idea. So if you've installed this, or when you install this, if you choose to do it, MPI run should exist as something within your Conda environment. And this is where I've installed my Conda environment for my machine. And again, MPI number of processors tells you how many processors to use, right? You typically will use the number of computers you have on your machine, right? Now, if you have 1,000 cores, you may not want to use them all because maybe the efficiency isn't there. But typically for a laptop, you just want to use them all. On a cluster, you'd want to use the number of cores that you've allocated to yourself on how to use it. So let's dive in. Let's take a look at the code and you can sort of see what's going on here. Here is our first MPI program. What you do is you first bring in the library. So MPI for Pi, import MPI. That brings in a namespace that's going to have all the stuff that you need for a message passing interface. I talked about a communicator. So this is a group of processes and how they're going to know about each other. The default communicator, which is the communicator of all the processors, is just called the world communicator. So it's COM world. So what we do is Almost all MPI programs start off with this. And it gets the communicator. The communicator is the one that is able to tell a program what processor or what rank you are running on. Are you the first one, the second one, the third one, the fourth one? There is a function, this is part of the MPI standard, called getRank, that tells us what number it is. Okay, so what I can do is I can run this and I can say my rank is, and it's going to be a number, 0, 1, 2, 3, 4. Okay, so I'll just do this one. So if I put this code in the file called com.py and I run it, okay, it says my rank is 0. Okay, Python is serial by default, and so if you run it, what it will do is the program will do this line. It says, okay, I'm the first processor, and since I run in serial, I'm all by myself. That's it. But if I do MPI run -n, it depends on the syntax. I use NP because of other systems, but I think -n will work as well. I could run this program twice. Oh, it's not script, com. Okay, so MPI run, what that's doing is it's spawning 2 separate copies of Python. Each copy of Python is going to run on a different CPU, but they know about each other through this communicator. So when I run this, one processor is running Python on one machine, and it says, okay, communicator, what's my rank? And its rank is 1. And the other processor goes and runs and says, okay, well, what's my rank? My rank is 0, and it spits it out. If you had 4 processors, right, it goes and does that way. Okay, now there might be something a little bit odd about this as I run this program, right? I just run the program 3 different times. The first time it said my rank is 1, 2, 3, 0. The second time is 1, 2, 0, 3. And the last time is 0, 1, 3, 2. I'm running the program 4 different times on 4 CPUs. They are all independent. The only way they connect to each other is they're all part of the same communicator. So they have some idea that there are other copies of it running, but they're running independently. Because my computer is doing other things right now, like talking to you over Zoom, the processor that particular program is running may run a little bit faster or slower, depending on which CPU it gets allocated to. That means the order in which these print statements actually get to the screen is not unique. It's not uniquely determined. There's a stochastic thing going on here. The order in which these things occur, like how many exact nanoseconds it takes, depends upon the overall machine. It means that when you're looking at an MPI program, you can't guarantee which program is at what particular line at any one time. It so happened that the first time I ran it, processor 1, 2, 3 got done in order, and then 0 was last. But then this third time, it actually was processor 0, and then 1, then 3, then 2 that got done in time. So the order in which these things are run is not determined ahead of time. But that's basically the way that it works. Now, I could keep on going up into a higher number. If I go for a much bigger number, so I went for 8 cores, it's going to say there are not enough slots available in the system to satisfy the 8 slots that were requested by Python. And it explains a slot is basically somewhere you can attach it. For a desktop or a laptop, it's the number of cores. If you do ls CPU in a Linux type environment, I think that'll work in a Mac OS X as well. It tells you what your CPUs are. So on the machine I'm talking to you with right now, it's an Intel 86 architecture, 64-bit. I happen to be running a Core i5 9600K. I actually think this is a pretty good CPU. I'm pretty happy with it. But it only has 6 cores and 1 socket. So I'm maxed out at the number of cores. I can't run on this computer any more than 6 concurrent processes at any one time. You might have a 4-core computer or a dual-core computer, or you might be on AceNet and have a 24 or 64-core node. Whatever you've got access to, you would just get this number all the way through. Okay, let's be a bit more fancy. Let's just not say a program which just says, who are you? Let's do some sending of data. Okay, how do I actually send data from one to another? So here's a program, okay? So the program starts off the same way. It initializes an MPI 4P, it gets its rank. And the idea here is all programs are doing the same thing line after line. Rank is their way of knowing which program they are. So the 0th rank is going to be treated a bit special. It's the one that's going to define some data. So let's just pay a dictionary. A is 7 and B is 3.14. It's going to send that data, this packet of data, to a destination, another rank in this communicator. And then I'm going to print out a message that says rank 0 sends that data. Now, another program is going to come along and check its rank. It's going to say, if rank equals 0, go, no, my rank's not 0. My rank's 1. Is my rank equal to 1? Oh, it is. Okay, I'm going to call com receive. So send and receive, those are those blocking points I'm talking about. And it's looking for a message from the source of rank 0. So it's going to sit here and wait for a message from rank 0. And when it gets it, it's going to print it out. If it's not rank 0 or rank 1, it just follows this part of the loop and just prints out a message and nothing happens. So if I was to run this program with 6 communicators, right? Rank 3, 2, 5, and 4, they very quickly jump to here and print things out. Rank 0 sends this information. Rank 1 receives this information. Okay, now I'm going to run this a number of times. Okay. The order in which things happen is still random, but not completely. Okay. The order in which ranks 5, 4, 3, 2 do their thing, that can be completely scrambled. It doesn't, there's no preference all the way through here. But it will always be the case that rank 0 will send before this thing receives. Now, the two things actually happen in concert, but basically this thing will finish sending, and only when it's finished sending can this thing start receiving. So rank 0 is always a little bit ahead of rank 1. So as we run this again and again, it's always the case that rank 1 is always right after rank 0, right? Or after in terms of sequence of time all the way through. Now, you don't have to send just dictionaries. In MPI for Pi, anything that can be pickled or basically compressed in any Python object that can be put into a data structure called a pickle can be sent over, but you can send more basic things. You can send just integers. So if you were doing integer sending, I could have some data. It should be a number. And I can send that data over the wire and receive that wire. When we're sending these single pieces of data, whether or not it be a pickled dictionary or a number, MPI standard uses a lowercase s here. And what this means is it's sending it in one go, one burst of memory. It's appropriate when you're sending a small bit of data to another machine. It just sends it as a thing, as a unit, as a single transfer. There's another way of sending in the MPI standard. They're not lowercase s, but capital S. These are called buffered sends. Okay? So here's a slightly more complicated one, and it's going to use this idea of a capital S send and a capital R receive. Okay, let's just look through the program first, and I'll try and show you how it works. Same startup. We're going to have so many processors. They're going to know whether or not they're rank 0 or rank 1. If you were the rank 0 processor, you're going to run this program line by line by line, and if you happen to be rank 0, then this is the code you're going to do. What's the code? You're going to do num data equals 10. Send that to the other processor, destination equals 1, and this is going to wait until that message is received. The other processor runs this line, runs this line, runs this line, runs this line. It's not rank 0, it's rank 1, jumps down to here, goes, oh, I am rank 1, and receives the data, the information that was sent from the first rank. This line will wait until this line occurs. So these two lines basically occur simultaneously. Okay, then rank 0 can continue and allocate an array. So say it allocates 10 numbers from 0 to pi and puts these into an array. Rank 1 prints out the number of data elements it's going to receive. It creates an empty bit of memory that's the right size. It's something where it's going to receive the data. So you've sent out that I'm going to send you 10 numbers. Number one says, okay, I'm preparing to receive those 10 numbers. And it's going to allocate in its RAM enough space to send that data. Now, you typically wouldn't do this with 10, but you might do this with 10,000 or 10 million numbers. It's going to allocate that memory. And then we're going to send the data. We're going to send this array, 0 to 3 pi, to here. The reason we use the capital S and the capital R is it's not going to send that data all as one chunk of information. It's going to break it up and send it over what's called using a buffer. Basically, it's going to take this data and break it up into pieces and send those pieces over the network piece by piece by piece. And that data will be received piece by piece by piece. If you're sending large data, these buffered sends and receives are just going to be faster all the way through. Okay, so let's take this piece of code. I'll just run it with 2 processors. And this one is called send array. Okay, so rank 1 printed out number of data to receive, 10. That's this thing. And the data received was the array, 0, 0.3, 0.61, all the way up to 3.14. So the point here is I've run 2 different programs. I sent information in one direction, and I waited for it to receive by the other direction. Okay, let me just demonstrate something to you. Let's say that I was to run this with only one CPU. Invalid rank. Oh, it doesn't even let me do it. Oh, okay, so it's failing because it's saying, I don't know how to send to destination 1. That doesn't exist. It's not running all the way through. So it don't even fail to do it. But let's put a mistake in here. What happens if we were writing this program? Also, I'll just change it here, send array. What if we were to make a mistake and forget Okay, here we go. Suppose this was your program. Rank 0 chooses the number 10, sends the data. Then it creates more data and sends it along. Rank 1, right, just says, oh, no, I already know the number's 10. I don't need to get it. I just know it's 10. It's always 10. It's fine. I'm waiting to receive the information. Right? Let's take that modified program and take a look at what it would do. Python. I'm confused by that. That's not correct. Oh, okay. I think what's going on is this first send is actually being picked up by this receive. And then this send was able to continue sending stuff along. But you see how it's broken. It's not working the way you're expecting. We're expecting to get an array of a bunch of numbers, and we never got those numbers all the way through. Anyways, point is you need to line up this communication so it works. Okay, the other kind of communication, not just point to point, would be collective communication, where you have some information and you want to send a copy of it to all the other machines on your system. This is an example of this would be broadcasting. Okay, so here's the code. Same setup. And what we're doing is we're sending information to all the other ranks on the system. So rank 0, we're going to choose that to be sort of the root rank of the broadcast. It creates some data. So this is just a Python dictionary, key 1, key 2, 1, 2, 3, ABC, XYZ. It's the input data. Rank 0, the first process on the first rank, knows about it. If you're not rank 0, data is just assigned to the variable none. And now all programs run this line together. They run the function bcast. And what that's going to do is take this data. If it is the rank of 0, it's going to send it. And if it's not the rank of 0, it's going to receive it until everybody has a copy of it. and then the program can continue on. Okay, so if I was to do this, MPI run bcast, I can send that dictionary, right? And so rank 0 has a copy of the dictionary, rank 1 has a copy of the dictionary. If there were 6 processors in my communicator, all of them have the data together, 0, 1, 2, 3, 4, 5, 6, 7, right? Now, you'll see the timing. See how rank 0 is at the top? Rank 0 is at the top. I'm going to speculate that rank 0 will always be at the top, and all of these other ones are going to be in a random order. That's because to broadcast the data from the 0 is really fast. The data is already there, so it completes faster. All the other Python processes have to wait to receive that data. So now the data might not be a dictionary. The data could be some array. So you could always broadcast the data as an array. So here's another variation of a program similar to what we've done before. Create some data on the rank equals 0 node. Create just an empty pointer on the other ones. Do a broadcast to broadcast the size of the array. Okay. And only if the rank is not 0, create some empty memory to hold it. So now this gets a little bit tricky. On rank equals 0, data is the sequence of numbers 0 to pi, there's 10 in total. If the rank is not equal to 0, then data is just an empty piece of memory. If we use a capital B bcast, what that will do is with buffer sends, it will ensure that at the end of the day, the content of data from rank 1 has been replicated inside the memory of all these other ones. So that's an idea of broadcasting the data out there. So if I was to run this data, you can see that rank 0 has the information, but then rank 1 has the information, rank 4 has the information, rank 3 has the information. You send it all out. You don't always want to send out all the information. Sometimes what you want to do is you want to take some information, split it up into pieces, and have each rank get only part of the information. This is what a scatter is. So we've got the information. It might be an array of, say, 400 elements. Every node wants 1/4 of all the elements all the way through. So what that would mean is you'd use a scatter operation. So here's what the code would look like. Same setup at the beginning. We're going to figure out our communicator. We're actually going to figure out how many other things are in the communicator, how many other programs are being run concurrently. If you're at the 0 rank, if you're that first processor in the list, you are going to create an array that goes from 1 up to size times number of data per rank. So if you say had 4 processors and size was, so if size was 4 and number of data per rank was 10, that means you actually have a data set which goes from 0 to 40, right? That's how much data is in here all the way through. We're just creating a problem where the amount of data is scaling with the number of processors. Every node runs this receive buffer thing, but it only allocates locally a portion of the total data. So it doesn't allocate in RAM this big amount of data so that's all 40 numbers. It only allocates 10 spots in memory to store a portion of the array. Then you do a capital S scatter, which takes the data from the root and splits it up so that every rank is getting part of the data, and it gets placed into this receive buffer. So let me run that program and I'll show you what it does. If I do an MPI run, let's do 2 Python, this is a scatter. Okay, so rank 0 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Rank 1 has 11 through 20. So the data has been split up from 0 to 20 into 10 into different pieces. If I run this over 6 processors, okay, rank 0, 1, 2, 3, 4, and 5 are each getting their own 10 starting points. So you can imagine if you were running a program where you wanted to vary parameters, you could use MPI to drive this program in a way that every copy of this program would get its own starting information, and it could go and do its own thing. This is how you achieve parallelization. Now, the only thing you want to do now is, now that they've done something, maybe you want to bring all the information back together, right? And this is what a gather is. So a gather takes information that happens to be in many different things, pull them together so that you're all done, okay? So what would that be in terms of an example? Is you'd say you have some data, right? Here, every single node is creating 10 pieces of data by itself, okay? So sequence of order here. Every process runs com, every process runs size, every process runs rank, every process creates a linear space, but it's written in the sense of going from 1 to 10, or from 11 to 21, or from 11 to 20, or 21 to 30, all the way through. It's only a portion of the data. Then only if you're receiving the data, you're going to create an array which is number of size times 10 big, and gather all that data together. So it's flipping a scatter on its head. So what you're going to do now is each one of those nodes creates some information, and then the rank receives all the results. So this could be used, say, what this is doing is these 1 through 10s, these aren't just numbers. Maybe each one of these things is something that actually computationally took some effort, right? So these are, well, let's do cryptocurrency things, right? Proof of work. So rank 1 gives you all these answers. Rank 2 gives you all these answers. Rank 2 gives you all these answers. And you bring them all together, and then you have all the answers together. But rank 0 didn't have to do the work for each one of these things independently. It could share it out all the way through. The final thing that's sort of in MPI would be this idea of a reduction, where what you want to do is you want to take this data. You don't really want all the data. You just want some part of it. Maybe you want the largest value from every one of these things, or you want the minimum, or you want the sum of all of these things. You'd use what's called a reduction. So in MPI reduce, let's say that you had rank 0, 1, 2, and 3, had the numbers associated with them of 5, 2, 7, 4. I could reduce that down so that I would get the sum. Or if I was to reduce down an array, it would add things up pairwise all the way through. And it's doing this in a parallel way. So MPI reduce is actually going to do things like multiplying, taking 5 and 2, bringing those two numbers together, 7 and 4, bringing those two numbers together, and then taking that 7, 5 plus 2, and that 11, 7 plus 4, bringing those two numbers together so you can compute the sum. So the sum itself becomes a parallel operation. So I'll just show you a quick example of that. Let's imagine that every rank has some number associated with it. And in this particular case, the rank is just its own rank. So value is a variable. It's equal to 0 for the first rank, 1 for the second rank, 2 for the third rank, and so on and so forth. What we're going to do is we're going to store the results, right, in a sum and a max. So this is a little bit of memory that's going to hold the result. Now we do the reduction, okay? So in a reduction, what's happening is the sum of everybody is being put into this variable, right? Now, it's only meaningful for the root. That's where the answer's sort of coming all in together. And so what happens is only rank 0 knows the value of the sum and the value of the max. Now, so what would that mean? It would mean, right? So, no, not reduce. Wrong code. Obviously, I copy and pasted the same thing twice. D20D. Yay. Nice thing about using. Okay, there we go. Oh, right, because I didn't run it with any other programs. Okay, so I sent 0, 5, 2, 3, and 4. Each program had it. Rank 0 is able to take those numbers and reduce them down to something. So in terms of running the program, maybe you didn't really care what these numbers were. You just wanted the best one, the max, or the min of all these different independent operations. You could use a reduction to bring it all together. Let me round this off with just an example of how you would actually use this maybe in practice. Let's suppose that you wanted to do some operation again and again and again. So in terms of pseudocode, right, you have 20 numbers and you want to take the square root of each one of those numbers. Okay, so in sort of normal programming, if I say range of 20, okay, so X is a range of 20. And if you ever want to take one of these iterators and take a look at what's inside of it, you convert it into a list. It's just the numbers 0 through 19. What a map does, I just bring in square root here. What a map does is it takes some function like square root and applies it to every element in this iterator. Okay, now map itself is like an iterator. So if I want to see what the values of it are, I have to sort of go through them. And here are the square roots of 1, 2, 3, 4, 5, up to 20. Okay. If I want to parallelize this, what we do is we take that list and we split it up into pieces. We take the number of ranks, chunk it, so that the first 4 or 5 go to one, the next 5 or 6 go to the other. And each chunk can be mapped independently. Okay. All 3 of these lines are running on every single node at the same time. So every node is only doing part of the work. And then you can bring it all together. Now, all reduce is sort of like reduce, but it means at the end of the day, everybody's got an access to the answer. I'm going to give you an example which makes a little more work to happen. So it's going to be not square root, but a square root with an extra little bit of work. And to make it pretend like an extra little bit of work, I'm going to use the sleep command. What sleep does is it waits for this many seconds. So if I have this program and I time how long it takes for my func of 20 to go, or let's do my func of 25, okay? It took 200 milliseconds of wall time, as in how long the clock on the wall would take to run. If I slept for 2.5 seconds, then it would take 2.5 seconds of wall time to actually run. So this is a way of artificially making a program run slower for the purposes of testing. Okay, so this program is running 200 milliseconds. If I didn't do this, square root is very, very fast. It takes microseconds. You're not going to see much. So I'm artificially making the program a lot slower so I can show you something. Let me show you the program in a serial way. So I think we've seen this idea before, where what I do is I use perf counter. Perf counter is basically just looking at the clock. So I'll just show you what that is. Time perf counter. Okay, it's just a number coming from the CPU that relates to how many clock cycles the computer's been on, or since some reference. So it's a nice way of being able to recognize how fast a machine is. Internally, that's how this is being done. But it just says, what's the current number of clock cycles? It's a counter. I can tell you that this is in seconds, and it has nanosecond resolution. So it's the number of seconds since I probably turned on my computer last. I think I rebooted it yesterday. Sounds about right. Okay, so let's do the start. Do this program. I did a range. We'll map, but what we'll map is we'll map my function onto X. So it's a square root with a delay, and then we'll list it. That's the program. And then there's some input output. Say I want to just display it on the screen. Okay. So here's how long this took to run. Okay. It took 4.007 seconds. Well, why 4 seconds? Well, I have 20 things. Each thing takes 0.2 seconds, a fifth of a second. So there's 20 of them. So it takes 4 seconds, plus a little bit. The little bit is the actual machinery of setting up the range and calling the map and doing the list, okay? Those are things that take a little bit of time, but most of the time is spent in the computation. So if I think about profiling, about how much time this function is working, if I could make this function run faster, my whole program would run faster. So it is totally appropriate that you spend some time trying to make my func just work faster. So if you were to come along and make it run twice as fast, right, then indeed the whole program would run twice as fast. But let's suppose, for the sake of argument, you couldn't do that, okay? This was as fast as the program were to run, and you just have to wait. Okay, now 4 seconds, you may go 4 seconds, I can wait 4 seconds, that's not so bad. But what happens if you wanted to do this operation on 60 numbers? It's gonna take, anyone know how many seconds it's gonna take? 12 seconds, right? Because every one of these things is taking 1/5 of a second. That's how long it takes to run. Okay, here is something we can parallelize. We can parallelize this using MPI, right? So what I'm gonna do is I'm gonna take this program and I'm gonna modify it so that it becomes a parallel version. So I'll show you the code up here. The beginning bit is the same as we've always done, okay? MPI4.MPI. I'm gonna define my program. It takes 1/5 of a second. So far that looks the same as a normal program. I'm gonna figure out how many processors are in my communicator and the size, and which processor I currently am when I'm running this program. Only if you're the first processor am I going to count the time, okay? The first processor is responsible for keeping the stopwatch. All the other processors don't need to worry about it because I want to know how long the program in total takes to run. Now we do the program. Let's take that data, and this is being run on every processor independently, but let's not do the whole thing. Let's split it up so that only a few get run on every one. So let's bring this thing up, break this up into chunks. So if there are 20 numbers and I apply this to 4 processors, then every chunk is going to be 5 things big. This line is different for every rank. For rank 0, it's going to take the data from 0 to 4. For rank 1, it's going to go from 5 to 10. For rank 2, it's going to go from 11 to 15, and so on and so forth. This operation is actually doing the mapping and making sure it really does the computation, right? But this is only occurring on a portion of the data. Then we gather it all back together. Basically saying, take the ends and send all the answers back to a rank of 0. We're now done. The rank of 0 is the one who's maintaining the stopwatch. It's the one that's going to print the output to the screen, and it's the one that's going to tell you how long things lasted. Okay, so we should always test our program first to make sure it's working. So this is the serial version of the program. Okay, and it takes 4 seconds. Okay, 4 seconds because we've got all these things going on. If I parallelize it and I run it with 2 processors, okay, then the program, the whole program, is taking half as much time. Okay? Now, if I parallelize this again and I run this with 4 processors, right, it's now taking 1 second. So this is pretty good. With 4 processors, it's taking twice as fast. With double the processors again, it's now 1/4 of the speed. Now, my computer is maxed out. I can't do any more than 6. So it's going at this speed. So this is what we mean by a speed up, okay? So what you do for a speed up is you take the amount of time it would take to run the program in serial, 4 seconds. You divide that by the number of processors that you're using, right? So 4 divided by 2, and you compare that to how fast the actual program takes to run. If this divided by 2 is this number, then you have perfect parallelization, your maximum efficiency all the way through. This is the best you can do. The absolute best you can do is cut this in half. But see what happens when I go from 2 processors to 4 processors, okay? I've gone from here, divide this number into 4. What's this number divided into 4? It's 1.00, well, 1.5. Notice how long the program's taking. It doesn't take 1.001.5. It takes 1.02. it takes slightly longer than 4 times faster. So it's still faster, but it's not been sped up by the same efficiency. Likewise, if you did this for 6 processors or 8 processors, what you're going to get is that same effect, where there still is a minimum amount of time it takes to run this program. There's no way around it. There is no way to make this program run any faster at minimum, because it has to, like, every unit takes 0.2. Like, the absolute fastest you ever could run this program for any number of processors would be 200 milliseconds. You cannot do better than that, because that's how much one component takes to run. This is sort of what Amadel's law, right? There's a maximum speed up you could achieve. You can't make, with infinite number of cores, things don't go infinitely fast. But this model could be reused to use multiple machines on your computer. So other than this little bit of MPI COM world stuff at the beginning, and this bit of ranking stuff, all this is really just normal Python, right? There's no specialness inside here. It's just a way of writing a program that lets you use multiple cores on your machine. There are other ways of parallelizing in Python. MPI would be used if you have access to a high-performance computer, array-based stuff, numerical things. There are other libraries out there, but this is what we mean when we say parallelizing a program. It's trying to figure out how to take this program and rewrite it in a way like this, so that it's able to take advantage of multiple cores at the same time, with the benefit of it now takes 0.8 seconds instead of 4 seconds. Why would that be useful? Well, that means that I now could run the program for more data. And even though before it took 12 seconds, now it's only taking 2 seconds. So I've sped things up. I'm able to do more computation on my machine. This is why we build supercomputers, and it lets you get to your science faster. So there's sort of an introduction to parallel computing and MPI, just so you've seen it before. You're sort of aware about what these arrows mean, and specifically what it is that going on behind the hood in a machine that looks like this. If you need this or want this, or you want to pursue this, AceNet, which is our sort of local organization that's affiliated with Compute Canada that runs these machines, they've got a ton of training available. So AceNet training, I'll just throw that on Slack for your benefit. Okay, so they've got a number of training events. And so what I'm going to point you to and this is if you're interested, these ones here are their standard series. So they typically offer these in person or on video sort of once or twice a year. But they've also gone and they've just put the slides up and a guy doing the video presentation. And it'll talk about what HPC processing is, what we actually have in AceNet and Compute Canada, basically going into more detail than what I've already done. To be able to use these services, you need to know how to use Linux. So you need to have a basic idea of what a terminal means and how to load files. This is what we covered. You need to know how to use the shell. You've already covered this because you took this course. You've done that. And then you need a way of running the program. I talked about MPI run, and that's part of it. But you also need to be able to schedule your job because it's shared computing. And on AceNet, they use a software called Slurm to submit the jobs in batch processing. I will leave that for those who are interested to take a look about what it means. It's how you actually run a program on a shared use all the way through. Now, this training thing actually has a number of other pages about how to do it, including some seminars on introduction to parallel programming, introduction to MPI programming. But I'm just going to show you, when you go to that slide, right? The reason I went with MPI for Pi is because here's what it would look like if you were doing it in C. You'd have these MPI inits and MPI finalize things popping all around. You'd have to compile it with a special compiler that's MPI aware. And this is how you would actually submit a job with Slurm or PBS. That's PBS, not Slurm. This is older slides all the way through. The actual code in Fortran or in C would have this look: MPI init, MPI com rank, MPI com size. This code is the same thing as my com.py, where I've got a rank and a size. All the API calls are sort of equivalent. And if you had something more complicated, so here's the equivalent of a program that if it's not rank 0, it sends a message to rank 0. Or sorry, if it's not rank 0, it prints to the screen what it is. If it's, no, I'll flip it around. It's printing to the screen, hello process 0, and it's sending a message, a bunch array as a buffered send to rank 0. And then rank 0 is doing a loop where it receives information from each one of those back all the way through. So this is what a C program looks like. And my point is, the thought of MPI is identical, but the complexity of writing in C or in Fortran, it gets more wordy. So you're more than welcome to take a look at this. Maybe you'll take an example like, how would I do an integral? An integral is a problem that works great in it with MPI. What would that look like as I coded it up? Well, you could do this in C, you could do this in Fortran, but maybe if you just want to get the feel of it, maybe what you want to do is look at this, read this code, and see if you could write this with MPI for Pi and get it to work. And if you can, you're like, yeah, I got an idea of what this MPI for Pi stuff needs to do. Okay. And there's other ways of doing it. OpenMP is another parallel model, and other things. And there's a whole bunch of other tutorials and coding things here. These training are good, but what's far, far better is the people who are actually behind this. So AceNet exists as an organization. Who are they? They exist to help you as researchers, if you're doing a research-based thing, actually use this infrastructure. So this team of people, right? These guys right here, these are people who get money so they can run it. These people are research consultants, okay? These people, their job is to be reached out to and say, hey, how do you do this? Oliver is at Memorial. So if you have a computational issue on AceNet, or really in general, and you don't get support within your own department, you may want to send this guy an email and be like, hey, Oliver, I'm trying to do something on AceNet. And if he can't answer, we have a second person. Grace is doing this now as well. We have 2 people in Memorial. They're both able to do this, but really anybody in this team can help support this kind of stuff. So I am going to encourage you that when you're getting into computation, getting into using AceNet or any other sort of advanced computing, take advantage of this team. Okay, it's not like they're working, but they're serving us. We're the market. So when you're doing something like you're trying to do computation, trying to use AceNet or something else in Compute Canada, please fire off emails to these guys to let them know what to do, and they can do more than just answering a specific question. If you're like, I'm not sure whether or not to use OpenMPI or use OpenMP or Kudo or CUDA or some other technology, this is what these guys do. So please take advantage of that if you're doing any sort of high performance computing and are even thinking about using Compute Canada as a resource.